Welcome back, everybody. We're in chapter 10 now on circular motion. Motion in circles is kind of interesting. It still follows Newton's second law that force equals mass times acceleration. But we're going to see that one thing that we never had to consider before is whenever you have a force, you're going to have acceleration in the same direction as that force. So because we always acted in straight line forces, that didn't become apparent. But if I have a force pushing on me, I'm going to accelerate forward. If I have a force pushing against me on my front, I'm going to accelerate backwards. So an acceleration is always in the same direction as the force. Now this becomes very apparent when you're moving in circles, because sometimes you can't tell where the force is coming from. In the case of the Earth going around the sun, you have this idea that the sun is exerting a gravity on the Earth, but what's causing the Earth to go in a circle instead of a straight line? It turns out that acceleration is towards the middle because the force is towards the middle. The gravity of the sun on the moon, or sun on the Earth, is actually what's causing the Earth to keep moving towards the middle. And so you end up not moving in a straight line, but moving in a circle. Okay? So if there was no acceleration towards the middle, the Earth would go in a straight line forever at a constant speed, just like we saw with Galileo's inertia. So there's some really good questions here. I think that this could really help you understand circular motion beautifully. All right, the main thing I need you to remember is acceleration is in the direction of the force. So wherever the force is, that's where acceleration is happening. Acceleration's in the direction of the force. All right, so they're going to ask you a couple different things. They're going to ask you where the velocity is, where the acceleration is, and where the force is. Okay, and sometimes it's not apparent. You're going to have to think. All right, so easy questions. You're at a car at a traffic light. The light turns green and the driver steps on the gas. Okay, so you've already got the situation where towards the right is towards the front of the car, left is towards the back of the car. If the car is moving forward, its velocity is in the forward direction. If you're getting faster, acceleration is also in the forward direction. Because positive velocity, we're going to say velocity is towards the right is positive, velocity towards the left is negative, acceleration towards the right is positive, acceleration towards the left is negative. Okay, so acceleration can be thought of as speeding up, frontwards or backwards, or slowing down. If you have a negative acceleration frontwards, it means you're putting on the brake. So we'll see all of these in a second. All right, so the driver steps on the gas. Your body lurches which way? Okay, so think about someone bolting the gas. Where does your body go? It goes against the back of the seat, so your body lurches backwards. Does that mean it's accelerating backwards? No, the car is accelerating forwards. The car is getting faster in the forward direction, so A is towards the right, so acceleration, the car accelerates forward, and the force on the car, remember, the direction of your acceleration is the same direction as your force. The force is making you accelerate forward, then the force is acting forward. Okay? Now, since you don't want to move, you want to stay still. An object at rest wants to stay at rest. So you're at rest, the body moves, the car moves forward. You want to stay still, so your inertia is making you lunge backwards because you want to resist that change in motion. So the sketch shows the top view of the car with forward being to the right. Note the directions of the velocity and acceleration vectors. So acceleration is going to the right, velocity is to the right. Next scenario. You're driving along and approach a stop sign. The driver steps on the brakes. Okay? So you put your foot on the brake. Is the car going backwards or forwards as you're slowing down? The car is still going to go forwards. So this is velocity. Velocity will go towards the right. It'll be a positive velocity. The velocity is getting lower and lower, but it's still positive velocity. I'm not going backwards. I'm still going forward, so I'm just going slower. The car is accelerating how? So let me see. Oh, first of all, your body lurches what? When you step on the brake, your body is going to be lurching how? Forward. Okay? So what's happening is you step on the brake, you're changing the acceleration. You are decelerating. That means my acceleration is not positive, but it's backwards. It's negative. So acceleration is actually going to be back towards the back. So in this case, velocity and acceleration don't have to move in the same direction. But what did I tell you at the beginning? Whichever direction acceleration is, that's where your force is. Force is in the same direction as acceleration. So if you were to look at F equals ma, okay, all right, if A is positive, say to the right, force will be to the right. If F is positive, A will be positive. They go up and down together, so they will act together. So you have velocity acting to the front and acceleration to the back. So number B, the car accelerates backwards. Okay, so it's a negative positive. A positive A would mean you're speeding up to the right. A negative A will either mean if you were stopped and you have a negative A, you'll speed up to the left. But if you're going forward at a negative A, or forward at a velocity, it'll start slowing down your velocity till you eventually get to zero, and then if you keep that acceleration to the left, it'll start going that way. Think of throwing a ball straight up. I throw with a constant velocity, gravity starts eating away the velocity until it eventually gets to zero. Once it gets to zero, it'll switch places, and you'll start accelerating in the other direction. Same thing will happen. Putting on the brakes is accelerating backwards. So if the force on the car is what? If the acceleration is backwards, then the force on the car is backwards. Okay? So draw the vectors for velocity and acceleration we just did. It's moving forward, but it's moving forward slower. That means it's changing its velocity. It takes a force to do that, so the force is acting in the other direction. If velocity were getting faster and faster, then acceleration would be in that same direction. But since it's being eaten up, acceleration is in the other direction. And you can think of throwing a ball straight up as an example. Okay, number 3. You continue driving and round a sharp curve to the left at a constant speed. Okay, so you're now going at a curve. You remember you change the acceleration if you change the speed, or you change the acceleration if you change the direction. Remember, you have acceleration is a change in velocity over change in time. Well, velocity is a vector, meaning I'm going in a certain direction. Acceleration is a vector too. That means in order to change accelerating, I'm accelerating when my speed changes, either up or down, or my direction changes. So I can accelerate even though I'm going the same speed. If I turn the steering wheel, I've changed the velocity because I've changed the direction that velocity is moving. And if I change the velocity, I've changed the acceleration. And that's what change means. If I change the vector velocity at all by changing direction or speed amount, then I've accelerated, either up or down, positive or negative. Okay, so going around a curve, that's why you feel like you, especially if it were a slick road, you feel like you're going to go off. And you could go off if you don't have enough friction on the tires. So if you go around to the left, which way does your body lurch? Okay, your body leans outward. Okay, when I was little, I used to squeeze my little brother against the door every time we'd go around a curve, and I'd say it wasn't my fault. It was the car that was making me do it. I'm bad. Okay, number 3, B. The direction of the car's acceleration is. Okay, now, if I'm slinging, let's go back here. If I am accelerating forward, I lurch backwards. Okay? If I accelerate backwards, I lurch forward. If I lurch to the outside, which way am I accelerating? I'm accelerating to the inside. If I'm accelerating to the inside, where is my force directed? F equals ma, and A and F are always in the same direction. Okay, so force is moving to the middle, acceleration is moving to the middle. This is called centripetal acceleration, and centripetal force is any type of a central force. It's a force that's moving towards the center, and that force is causing acceleration towards the center. And if I have acceleration towards the center, then my velocity is constantly changing and I move in a circle rather than moving in a straight line. Okay, so 3B. 3B says the direction of the car's acceleration is, we've already drawn it, inward, because I lurched outward, and so we draw the vectors. Now where's velocity? My car is going forward. Okay, so velocity is forward, and my acceleration is inward, and so I'm ending up with some kind of a vector between them, and that's turning the car, turning the car, turning the car. If I had no acceleration in, I would go straight line. But by turning the steering wheel, I have an acceleration in, and then I keep turning, keep turning, keep turning, keep turning. And it's actually the friction on the tires that's causing that force. It's the road pushing on the car, but it's pushing on the car inward because of the friction of the tires. All right? This is hard for a lot of people to understand, but you can feel it. Like just riding in a car, you know where your body wants to move, so you can almost figure this out just from your experience. All right? In general, the directions of lurch, that's how your body moves, and acceleration, and therefore the directions of lurch and force, because force and acceleration are in the same direction. So lurch and acceleration, or lurch and force, are the same, or they not related, or are they opposite? Okay, if I accelerate forward, I lurch back. If I accelerate inward, I lurch outward. So they are always opposite. All right, now more practical. A whirling stone's motion, direction of motion keeps changing. Okay, so I'm moving it around and around and around and around. I could move it in a constant speed. Okay, I'm moving my arm at the same tension all the time, and so it's going around at a constant speed. But what's changing with the velocity? Remember, acceleration is a change in velocity, which is a vector over the change in time. Okay, so what's happening is this wants to go in a straight line, but there's a force towards the inside, and it moves it a little bit. And then it wants to go in a straight line. So it wants to go here, but then it's tugged, and so it moves here. Now it wants to go here, but it's tugged, and it moves here. And then it's tugged, and it moves here. And so it's constantly going in a circle. And it's going in a circle because the tension in the string is pulling it in towards the circle all the time. It wants to fly away because it wants to keep in a straight line path, but the tension in the string were to keep going, keep going. If that string tension would break, if that string would break, or you let go of the string, immediately that stone or whatever would go in a straight line in whatever direction it was moving at the second that you let go. So this says its direction keeps changing. If it moves faster, its direction changes what? Okay. If the stone moves faster, is it changing direction slower or faster? Okay. The faster it moves, the faster it's changing direction. So it's changing its direction faster. And if it's changing its direction faster, what happens to the acceleration? If this is changing faster, what happens to the acceleration? You're accelerating either up or down faster. So either this number is getting bigger faster, or it's getting slower faster, depending on which way you're doing it. This indicates that as speed increases, so now it's not slowing down, it's speeding up. Okay? As speed increases, acceleration also increases. I hope you can see that. Now consider whirling a stone on a shorter string. Okay, so you have a smaller radius. What's going to happen? For a given speed, the rate of the changes is what? For as this gets smaller, 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 it's going to move how? Think about being on a merry-go-round. Where does it feel hard, or where do you feel the bigger pull, or where do you feel the littler pull? Or you could just do a mind experiment. Shorten the string. What's going to happen to the time it takes to go around? Is it going to go longer as the string is shorter, or is it going to go faster as the string is shorter? Okay, you have enough experience just by being alive that you could figure that out. So what's it saying? For the given speed, the rate of the stone's changes is it's more. If you shorten that string, that ball will speed up. Okay, because by shortening the string, you've actually increased the tension. By increasing the tension, you've given it more reason to change. The tension is the force moving in. It's the centripetal force. B says this indicates that as the radius decreases, okay, as it gets shorter, okay, then the tension's going to build. If the tension builds, acceleration does what? It increases. Okay. Please think as we do this, all right? I need you to think, not just write down. Thinking is the only way that you're going to learn this. Okay. So here's some more examples with centripetal force. Remember, centripetal force is an inward force, okay? An inward force that causes an object to move in a curve, okay? And in the case of this situation where the tension is exactly the same all the time, it'll move not just in a curve, it'll move in a circle, okay? So here's your first scenario. A rock is tied to a post, moves in a circle at a constant speed, frictionless horizontal table, okay? So there's nothing dragging it. So the weight of the stone on the table creates weight. The table pushing back is a normal force. So these two are countered to each other. But I also have the tension in the line. If that string were to break, the ball would fling off the table. Since it's going around in a circle, I've got a force moving inward caused by the tension. All right, so this says all the forces acting on the rock are shown. Tension T, support force N by the table due to the force of gravity W. Okay, all three are acting. So here's the first question. The vector responsible for circular motion, okay, is it its weight causing it to go in a circle? Is it the normal force causing it to go in a circle? Is it the tension that's causing it to go in a circle? It's absolutely the tension. That pull towards the middle keeps wanting it to, it wants to go straight, but it doesn't. It curves slightly, and then it wants to go straight, but that tension keeps pulling, and it keeps turning, and eventually moves in a circle. So the net force on the rock is not N and W. They cancel each other out. This is going into the table. This is coming from the table. The net force is the tension. The net force, remember, is causing acceleration. If you have F, okay, that's unbalanced, and on any mass, you're going to accelerate that mass. So even though you could go at the same speed, it's not changing its speed, it's going at a constant speed, you're constantly accelerating because you're constantly changing the speed. As you change the direction of the speed, you're changing the speed. Okay, the direction is the same. It's part of that speed because it's a vector. It's not just a magnitude, it's a magnitude and a direction. So if you change the direction, you've changed the speed. If you've changed the speed, you've accelerated. Okay, so F equals ma. This tension is causing it to accelerate, and that's called centripetal acceleration. Here's the next one. In this case, the rock is tied to a string and swings in a circular path as shown. So it's going around and around and around and around. You're slinging it like David's stone. It's not resting on a surface, so there's no friction. Use the parallelogram rule to find the resultant of T and W. Well, you remember when you do a parallelogram, you want it to be in the same, okay, two things parallel to each other, and so you're going to end up with a force resultant, this is R, resultant, and it's moving in towards the center at the same plane as the circle is moving. Okay, so the tension and the weight together come together to make a resultant, and the resultant is centripetal. It's making this move in toward the center that's keeping it moving in a circle. It's the resultant force here. So what's the direction of the resultant of T and W? Okay, it's towards the center. So if you have a force moving towards the center, you have a centripetal force. That's what that's called, centripetal. Does the resultant lie in the plane of the circular path? Yes, it's the same plane as the path. So yes, it does. Is this resultant also the horizontal component of T? So remember, horizontal is like the same as the horizon, and it's part of T. Okay, it's part of T. Remember, this is a, you could think of it as a right triangle. Some of it's going straight up, some of it's going straight in. So yes, it is. It's part of the tension. So that tension is what's causing it. It's what's causing it to have partially resultant because of its weight, and it will move in a circle. So let's imagine making this 1,000,000 times heavier, Okay, do you see that? Then your circle is going to be very, very slow, and it takes a lot of, it would increase the tension a lot, but the resultant would also be increased. Is this resultant also a horizontal component of T? Okay, yes it is. Okay, so the resultant is horizontal component of T, and it lies in the central path. Is the resultant of T and W, or the horizontal, it's saying the same thing, a centripetal force? It is a centripetal because it's acting toward the inside, which is making the rock move in a circle. Otherwise, the rock would move at a straight line wherever the velocity is going, wherever it's headed. Okay. In the case shown on the right, the rock rides on a horizontal disc that rotates at a constant speed about vertical axis. Okay, so this dotted line, it's going in a constant speed around, oh, it's going this way, round and round and round. Friction keeps it from sliding, so it stays on the circle, moving at a constant speed. Okay, so I want to know where the forces are. So it's sitting on the table, so it must have a weight. The table's pushing up from it, so that, remember, is called a normal force. Where's the other force? Well, it's not moving straight. It's not slinging off the table. So there must be a force that's keeping it going in a circle. And so its force has to be moving towards the inside. Okay? And this force is actually friction, because that's what it said. It's friction is keeping it from sliding. So friction, just like when the car was going around the curve, the tire's friction is actually what's making the car go towards the inside. Otherwise, if the car was sliding on ice, it would sling out of the circle. It wouldn't go around the curve. It would just sling off into the side. That's why icy roads around corners are especially dangerous. Same reason. So draw a label for all that act on the rock. There's the labels. Which force is centripetal? Which one's acting towards the center? Okay. Well, we just called it F. It happens to be friction, but we just called it F. Which force provides the net force? Well, these two cancel, right? The normal force and the weight are canceling each other out, so they are not, they're not a net force. This is the net force, and if you put a net force on a mass, you accelerate it. F equals ma. So a net force acting on a mass accelerates that mass. So which force provides a net force? The F does. Why do we say that the net force, not say that the net force is zero? Okay. Well, because these two would cancel out. If it were not moving, it would be zero. It would be a net force of zero. But this is not balanced. This is not countered in any way. So we would say it's accelerating inward. Otherwise, it would sling off. If it's moving in a circle, it must be accelerating inward. So the how do I say it? Centripetal acceleration or central acceleration. Centripetal is the word. Centripetal acceleration is not zero. Okay, so that means there is a net force, and that net force is making it go in a circle. Now the rock is held in place by friction against the inside wall of the rotating drum. So this is essentially slinging a drum around and around and around. There's amusement park rides like this where you stick to the wall and you can crawl around like a bug on the wall because you're being slung around like a washing machine. Makes me car sick, but some people like it. So what's shoving? What are your forces? Okay, I've got gravity acting down, so I have a weight. That's a W. And then, where's my normal force? Here's the surface that it's sitting on. So this is normal. Okay. And where's my other force? Is there another force? Okay. Yeah, the force is friction. Okay. And the friction is moving here, in this case, opposite to the W. Okay. Because you want to be slung out of the bucket. If you've ever stirred a ball in the bottom of a cup, it wants to sling out of the cup because the friction is actually pulling it out opposite to its weight. Okay, this is like a cup that doesn't have a bottom. So which force is centripetal in this example? The normal force. Which provides the net force? See, these two are canceled, and it would be the normal force. Okay. So for instance, if you stop slinging this, the friction would go away and the weight would drop and the ball would fall out. But as long as you can keep it spinning, you can keep it glued essentially to the inside of that drum. Last one, this time I don't have a drum, I've got a cone. Okay, so the normal force is acting kind of at an angle. This time it rests against the frictionless wall of a cone. Okay, so I don't have friction now acting on, so it moves with the cone. So as it slips and slides, as you speed up the cone, it'll go towards the top. As you slow down the cone, it'll move towards the bottom. So the rock does not slide up or down as the cone rotates. Okay, so we know that it's going at a certain speed so that it doesn't want to go faster or slower, so it doesn't go back and forth. Draw and label all the forces that act on the rock. Well, I've got weight. Okay, weight is acting straight down. I also have a normal force that's acting away from the surface at 90 degrees. And now I have to do one of those parallelogram rules, right? So I've got something like this, and I end up with a resultant. The resultant again is going towards the center. That's why it stays where it is. The resultant's moving towards the center, and so it's moving, changing, and accelerating towards the middle. That's why it doesn't sling up or sling down. Okay, so this says draw and label the forces. Okay, I did that. So this one would be the normal force because it's acting away from the surface. This is the resultant, this is the weight, and the resultant is the one that's making it go in a circle. Should the resultant lie in the plane of the circular path? So here's the circular path going around in a circle, and it does. It's in the same. Okay, so yes, it would lie in the same. And then why? Okay, what does the resultant do? It's going to provide the centripetal force necessary to keep it going in a circle. Okay, you really have to think about this one. I hope this helps.